We've been learning about regression. And last time we learned about simple linear regression. Now I want to expand on what we've learned from simple linear regression with something called multiple linear regression. Don't worry, we're not getting too far away from where we started, because no matter the topic, regression is fundamentally about making predictions. In fact, I had so much fun making predictions last time, I thought I might even try it again. I really do have an interest in predictions, the predictions and the errors specifically. So one thing I tend to do is, how at the end of the year, in December, people will publish articles in which they predict what's going to happen in the following year. I like to save those articles. I was just looking at a folder that I have called Predictions of 2024, in which in December of 2023, people made predictions about what was going to happen in 2024. And what I have noticed from just scrolling through them is sometimes people will get information that's going to happen in January or February, but they always miss things that happen later on in the year. And overall, the predictions are not terribly accurate, unless you make predictions that are just so broad that it's really hard for them to be incorrect. But before I start feeling a little too confident, if I keep track of how many times I have said something is going to happen and then it didn't happen, I probably shouldn't be as confident in my predictive abilities as I am, because I get it wrong fairly often as well. And that's really the case with predictions. Anytime you make predictions, there's always going to be error. And the best predictions are the ones with the least amount of error. The best predictors are the ones who get it right more often. Well, let me take an example of this. Start with something that could be used for prediction, and let's see how good I can make this prediction. Here's what I'm going to begin with. If I know this one bit of information, I might be able to predict how you vote. So my question is, do you own a Tesla? I want to predict which way you're most likely to vote. So I'm going to think about what I know about Tesla. If you drive a Tesla, chances are you're pretty tech savvy and probably also interested in the environment, because electric vehicles don't have the same environmental impact as gas-powered vehicles. I know that these vehicles tend to be fairly expensive, so if you can afford one, you probably have a good job, which means you probably got a good education to get there. I also know that these types of electric vehicles work better in cities than they do in rural areas. There's more chargers in cities than there would be out on the farm. So I'm going to put all those pieces together. You're smart, you're educated, you have some disposable income, you're tech savvy, you're concerned about the environment. I think if you own a Tesla, you're going to vote Democratic. That's my prediction. What do you think? Well, okay, I guess that's one way we could go with that. Although, now that I think about it, I have been seeing stories about people who had owned Teslas who are getting rid of their Teslas or selling their Teslas. And a lot of those people they kind of match that description that I gave you earlier. I even saw an article from NPR that described a pattern shift in purchasing. So maybe I need to revise my prediction. Maybe what I need to do is just predict with the mean. So if I want to predict the likelihood of your voting one way or another, Democratic versus Republican, maybe what I should do is just go back to the last election. Those numbers, I believe, were 49.8% to 48.2%. So I would say that if you own a Tesla, based solely on the average for voting patterns, you're going to vote Republican. So when I make this prediction, I should be right about 49.8% of the time, predicting only with the mean, the average. That's just the typical. In other words, I'm saying that owning a Tesla doesn't give me any predictive evidence, that doesn't improve my prediction with that. I'm going to be right more than I'm going to be wrong, but I'm still going to be wrong about half the time. Is that a good prediction? So here's what I need. I want some better predictors if I'm going to use Tesla ownership as part of a predictive model for how I think you're going to vote. Here's some things that might help. If I improve my predictors, and I ask not, do you own a Tesla, but do you own a Tesla Cybertruck? And are you male or female? And what is your age? Are you in that coveted 18 to 34 age group that the advertisers just love? And what is your primary source for information about the world and politics? And if that comes from listening to podcasts, I'm going to put those predictors together and say, if that matches you, then you're probably going to vote Republican. And I'll probably be right a whole lot more than I will be wrong because I have better predictors. Another thing that might help, however, is more predictors. So more and better predictors are going to improve the predictive validity of my model. My first prediction, or maybe it was my second prediction, where I predicted simply with the averages for voting, that would be like a null hypothesis model. I'm saying that ownership of a certain type of vehicle doesn't add anything to my predictive model. But when I add more predictors, now I can create a model that actually works better in that it's right more often than it's wrong. We started with this idea when we talked about simple linear regression. With simple linear regression, we have one predictor and one outcome. It's really mathematically, functionally the same as a correlation. I could take something that is known, let's say your measured level of stress, and use that to predict your blood pressure. Because we know that stress and blood pressure are correlated, we should see some predictive ability. People with higher stress have higher blood pressure. People with lower stress, lower blood pressure. And I could put that into a model. My model would involve a constant, b sub 0, and the addition of a coefficient, which is going to come from my predictor, and an actual value. In other words, if I know your level of stress, I can multiply it by this coefficient, add it to a constant, and make a prediction about what your blood pressure will be. However, that is a model built on just one predictor. I may be able to improve that, though, if I have more and better predictors. If I use not just stress, but stress and age and BMI together, I get all of that information. I may be able to predict blood pressure even better than simply using a single predictor. Now, ultimately, the way I'd be able to answer that question is look at the error term in my model. If there is less error in this multiple regression model than there was in my single predictor model, I know that I'm making better predictions because I have more and better predictors. We've talked about job satisfaction in previous applications, and we know that burnout can predict job satisfaction. There are other things that can affect job satisfaction, however. Compassion fatigue is a specific form of burnout that occurs among mental health professionals, really anybody in the helping profession. And that is, if your job is to help people who are in distress, that helping can have an emotional consequence for you as well. Just being exposed to that trauma and the stressors and the stories, the sad tales of people who have been affected by natural disasters or torture or some other devastating event that's happened in their life, that can have an emotional effect on you. There's also, however, the benefit of knowing that you have helped someone who was in distress. And that is called compassion satisfaction. So compassion satisfaction should increase job satisfaction, while compassion fatigue would decrease job satisfaction. And compassion fatigue is also a subset or specific form of burnout. So another thing I might be interested to know is whether compassion fatigue is really just the same as burnout or whether there is a distinction between them. These are things that I can answer by improving the complexity of my model. Simple linear regression involves a model like this. It has a constant, b sub 0. It has one predictor, which has a coefficient, b sub 1, which I would multiply by an x value that I would get from my x variable. In other words, tell me your level of stress and I will predict your blood pressure. Let's look at how the complexity of this model changes once we start adding multiple predictors. What you'll see is that although it gets larger, the model is just a repetition of what we've started with. So if b sub 1 times x sub 1 is our first predictor, our second predictor is going to be b sub 2, x sub 2. And the third would be b sub 3, x sub 3. Each predictor, whether that is burnout, compassion fatigue, or compassion satisfaction, each predictor is going to have its own coefficient. I would then multiply that coefficient times your score on that scale, add them all together, add it to our constant, and that would be my prediction. More and better predictors should lead to a better quality of prediction. Every regression model is always going to start with a constant. It's also called the y-intercept. It is a value that we get when all of the other predictors equals 0. So basically, drop out everything else in the model. That is your prediction. Sometimes this makes sense in the real world. We're going to do an example on one of the assignments where we have the line speed at a factory predicting the number of defective parts found. Now, in that example, how many defective parts get found when the line speed is 0? Well, you can have a line speed of 0. That does make sense. You're probably not going to find a whole lot of defective parts because the line isn't running. Or maybe you could say if we didn't run it through a line, we'd find all the defective parts. The point is, we're going to have a high degree of finding defects if we have 0 as our constant. But that doesn't do us a lot of good because we really do want to be running that line at a certain speed, and that's going to move these parts through. And then we want to figure out how many parts get discovered, how many defective parts get discovered when the line runs at various speeds. That makes a little more sense. However, if we're using variables like compassion fatigue and compassion satisfaction, those really can't have a meaningful 0. If I'm trying to make a prediction, let's say about GPA, it doesn't really make sense to predict GPA when IQ is 0. There is just no such thing. So what does that mean for our model? Sometimes the intercept makes sense in the real world, sometimes it doesn't. Sometimes the intercept is significant, sometimes it's not. The bottom line is we're going to need to leave that intercept in the model because it's necessary for the math. It's our starting point. Even if it doesn't matter in the real world, it does matter for the model. That said, if it is an element that has predictive ability, as evidenced by it being statistically significant, if it matters in the real world, that would matter in our model, and if not, then it wouldn't matter in our model. So basically, whether or not your intercept is significant is really a function of whether or not having a meaningful 0 actually means something. Now, the second thing that we're going to discover in our model are these unstandardized predictors. We know they're unstandardized because they are indicated by the lowercase b, b sub 1, b sub 2, b sub 3. We're going to report unstandardized predictors for our model. And the reason we're going to do that is because they're in the same terms as the thing that we originally measured. So for instance, if we're measuring something about education and something about dollars of income, when we say something like, for each additional year of education, lifetime income increases by $100,000, that is meaningful. That is interpretable. You can understand that. And you might think, well, if I stay in school another year, I'll get another $100,000. It doesn't work like that. It means that for every additional year of education, on the average, people who have that much more education earn on the average $100,000 more over the lifetime. But there's one other form of predictor that we'll find when we look at our table, and that would be a standardized predictor. And that's going to be indicated as this beta value. This beta terminology is not as easily interpretable because it works more like a z-score. I could say that a 1 unit change in stress leads to a 0.37 unit change in blood pressure. And you might wonder, well, what are those units and how do I interpret that? You won't interpret it directly. It doesn't really make sense directly. But it does make sense when I'm looking at other predictors. And I see that this one has a 0.46 increase. And that one has a 0.03 increase. It doesn't increase very much at all. And this is 0.37, the other one's a 0.48. That is easy for comparisons. So now instead of trying to interpret dollars or years or some other predictor, I can just look at these numbers. It makes it real simple for comparing between models. Now, every model has this error term, the residual error. It's the difference between what was predicted and what actually occurred. If you look at the number of predictions that a person on television has made, and they're wrong more often than they are correct, then next time you see that person make a prediction, you can be a little more skeptical about that prediction. They have a high error term. Versus if someone has a really strong track record of making predictions and they're almost always right, when that person makes a prediction, you better listen because they have a really small error term in their predictions. So I would love to see error terms on all television shows. If people are talking about things and they're going to assert that they know something, I'd like to see an error term of how often is this person correct versus how often is this person wrong. That kind of explains how we use error terms to determine how good our model is. If we have a really large error term, that just means that we can't be very confident in our model. If the error term is minimized, well, now we can be more confident. Our error term just tells us how trustworthy our model is, how good our model is. The best model is the one with the least amount of error. In order to understand multiple regression, we've got to understand partial relationships between predictors and outcomes. Now, we've studied this when we looked at correlation. Correlation has two scale level variables. If we think of that like a Venn diagram, we could just draw a circle to represent the predictor and the outcome, and then we could create a certain amount of overlap between those two circles. That amount of overlap represents the covariance. How much variability in one, or let's say the outcome, is predictable from the predictor variable. The larger the overlap, the more predictive ability. That is called a zero-order correlation, simply correlating two variables. The amount of overlap is the variance that's explained by the second variable. The amount of overlap represents the variance, let's say in blood pressure, that can be explained by BMI. It is the same as the R sub XY correlation, which we also saw in our regression model as being the coefficient B sub 1. If you only have two variables, the B sub 1 is going to be the same as if you've done a correlation to find the overlap between those two variables. If I want to add a second variable, I could also do a zero-order correlation. So now, instead of explaining blood pressure using your BMI, I could explain blood pressure using your age. And just like we saw in the previous example, there will be an overlap between these two variables, and that overlap represents the variance in blood pressure that is explainable by age. It is also a simple correlation. Now we have two zero-order correlations. However, with multiple regression, I'm going to put both of these predictors into the same model. That means I'm going to use both BMI and age to predict blood pressure. So we know that blood pressure tends to increase with BMI, and also blood pressure tends to increase with age. There is some unique variance in blood pressure that can be explained by BMI, and there's unique variability that can be explained by age. However, we know that age and BMI are also correlated, that BMI does tend to increase with age. In other words, there is variability between age and BMI that is shared, and it also explains our outcome of blood pressure. If all I do is create a model where I have both predictors predicting an outcome, and I simply explain all of that variability, it's like I'm counting this middle variability twice, because this is variance that has been shared between my two predictors. And essentially what I would be doing is overestimating the amount of variability, because I'm counting this big slice as variability and this one as well, and to whatever degree they overlap, that's being counted twice. What I should then do is deal with this overlap so that I can see what is the relationship between these variables, between a predictor and its outcome. The way that I do that is called partial correlation. In a partial correlation, I am removing all of the information from age that could predict blood pressure and BMI, leaving a correlation between X1 and Y, a correlation between BMI and blood pressure, in which age is statistically controlled. I have controlled for that variability. I might also say, what is the correlation between these two variables when this third one is held constant? Or you might hear statisticians say, when this variability is partialed out. That's where we get the name of the partial correlation. This is the pure correlation between these two variables, controlling for any other sources of variability, any other predictive element in my model. So now I'm getting the variance between BMI and blood pressure that is explainable only by the BMI. Partial correlation. It's important that you know about a variation of this, which is called a semi-partial correlation. Semi-partial correlation is the correlation between blood pressure and BMI when age is statistically controlled for BMI, but not for blood pressure. This is also called a part correlation. Part or semi-partial correlation, same idea, and the controlling for is going to be dependent upon what it is that we want to demonstrate with our model. We will be able to see both part and partial correlations when we do this example in JASP. So we're not there yet. We're not going to be using this example. We're not going to be using partial or semi-partial correlation, but we'll be using partial correlation. Every model, including multiple linear regression, is built upon certain assumptions. And if those assumptions are violated, the results that we get from our model might be misleading. So it's important that we understand what are the assumptions for regression before we actually run our model. The first thing we want to make sure of when we're doing multiple linear regression is that we have a scale level dependent variable. Our outcome is measured at the scale level. And the second thing is we want to look at our predictors and make sure all of them are scale level predictors. There are models, there are techniques that we can use in regression that use categorical predictors. Categorical, do you own this type of vehicle, yes or no? I would code those as 0 and 1. And that could be dropped into a model, and we can use that to predict some kind of outcome. However, in our example with multiple linear regression, we're going to restrict ourselves only to scale level data. Now, the second thing I always look for is whether or not we have a random identifier in the data set. This is not strictly an assumption, but it does make your life much easier. If you have this random identifier, it's going to make it much easier to find cases that are problematic. Like if a case is an outlier, we'll be able to spot it really quickly. We want to be sure that we don't have any missing data in our data set. We can spot this by looking at frequency tables. We run a frequency of each of the variables and make sure they all have the same sample size. In our example, we have 3 predictors and 1 outcome. All of them should have a sample size of 200. That was the number of people who were in the survey. If not, then we have missing data. We'd have to go find those missing data and decide if this person has not contributed, let's say, a burnout score. They didn't answer, or there was some kind of mess up with the coding. If they don't have a burnout score, it's really going to be difficult to include them in our model, so we might just want to drop out that case. And that is called list-wise deletion. Any cases with missing data simply get removed. Even better is if I could figure out what that burnout score would have been if this person had answered the items and we had that value. Now, how could I do that? What I would do, or one way of doing that, is looking at all the other variables. Are there other people in my data set who have answered similarly to the one with the missing values? And if so, we could reasonably assume that whatever they would have answered would be similar to someone who answered in a similar way. So we could fill in or impute that missing value based upon its similarity to others in the data set and the way that they answered. The traditional recommendation for sample size is 10 to 20 observations per predictor. However, some more recent articles, or recent article that I read, says that you need to have a minimum of 20 plus 5k, where k equals your number of predictors. We have 3 predictors. So 3 times 5 is 15, plus 20 is 35. The absolute minimum that we can have in this data set with 3 predictors should be 35. Now in our case we have 200, so we've way exceeded that minimum amount. But if we had fewer than 35, what could we do? Well, we could collect more data, and that would be the best approach. In fact, because 35 is the absolute minimum, we could collect a whole lot more data. We're going to get a much better predictive model for that. Or we could drop out predictors. We could simply remove the least useful predictor from our model. Univariate outliers are cases where when we look at our standardized residuals that exceed either 3 or 3.29, we'll say that is a case with an outlier. In this table, we can see that case number 472 has been identified as a univariate outlier. Now, univariate outliers, sometimes we leave them in, sometimes we take them out. But when we have multivariate outliers, then we have a case that just simply has to be removed. A multivariate outlier is an outlier not just on one scale, but on multiple scales. They're not just odd in one way, they're odd in a lot of ways. Multivariate outliers will be removed from the data set, and we would identify those cases using a Mahalanobis distance test. This is an example of a test that was run in JASP, and we would interpret that Mahalanobis distance value the same way as we would with a chi-square. Again, multivariate outliers are going to need to be removed. Linearity is an important assumption for any type of regression modeling. Let's look at a series of scatter plots. So when we look at job satisfaction versus burnout, there's a nice linear relationship between those two. And the predictive numbers, those are nicely spread out. So this is a good linear relationship. Burnout and compassion fatigue, yeah, that's a fairly nice linear relationship. Here's one, job satisfaction and compassion satisfaction. Generally a good linear relationship, certainly a strong positive relationship. Although if you look right here, there's like, I don't know, missing data. There's stuff that you feel like should be there, but it's not. There should be a lot of dots here. We don't see them. When we look at compassion satisfaction and compassion fatigue, we see that same kind of thing. First of all, not a very good linear relationship. It's just kind of like a big square. And also this missing quadrant up here in the upper right. we're a little suspicious of compassion satisfaction as a predictor. So when we look at this, we see good enough for us to do a linear regression model, but we're not going to be surprised if we see something weird going on with that predictor, the compassion satisfaction, because something about that just seems a little off. Multicollinearity can be assessed by looking at the collinearity statistics. The VIF numbers should be less than 10, and the tolerance number should be greater than 0.10. And because of the way the math is done on this, if the VIF is less than 10, then the tolerance will be greater than 0.1. And if the assumption is violated for one, it'll also be violated for the other. Now, multicollinearity means that you have two predictors that have so much overlap between them, they're essentially predicting the same thing. They're so strongly correlated that one of them is really unnecessary. It's redundant. And the way that you can deal with multicollinearity when you have a model like this is just simply drop out one of those predictors. So you may run across an example like that, I don't know, sometime in the near future, where you find multicollinear variables, two variables that are so strongly correlated that they're essentially the same thing. The solution, drop out one of those variables from your model and just use one as your predictor. If our residuals are normally distributed, we will see all of the dots lined up on this diagonal orange line. In this case, we would say, yes, that we have strong evidence for normality in our residuals. We could check our homoscedasticity, looking at whether the scatter plot for homoscedasticity is roughly elliptical or roundish. We don't have a cone-shaped or a bow tie shape with our homoscedasticity. Once we've checked all those assumptions, we are ready to actually run our model. We're going to be using the job satisfaction data set that we've used previously. So open that up in JASP, and then I'll walk you through the steps that will be necessary for actually doing a multiple linear regression with our job satisfaction data. Here is the setup for our analysis. A clinic administrator knows that burnout is associated with decreased job satisfaction. As burnout increases, job satisfaction decreases. But there's a theory that compassion fatigue is a special form of burnout unique to therapists or others in the helping professions. And on the other hand, compassion satisfaction, which is the good feeling that comes from helping, may improve job satisfaction. In fact, we saw that compassion satisfaction was strongly related to job satisfaction, so maybe it acts as some kind of mediator or moderator, or it somehow changes the relationship or helps to buffer the effects of burnout or compassion fatigue. That's what we're going to find out. In order to do this analysis, we are going to begin in the drop-down menus of JASP, go to Regression, and then under Classical, choose Linear Regression. We're going to move the variables of interest into their proper places. The thing that we are predicting is job satisfaction, so JS is going to go into our dependent variables box. The predictors will go into the covariates box, and they'll go in this order. First, move in burnout, then move in compassion fatigue, and finally, put in compassion satisfaction. We are entering all of our predictors as one big block. When we look at the output, we're going to be able to determine whether any particular predictor was statistically significant or contributing to the model in a significant way. However, theoretically, what we're looking for is the overall effect of all of these variables together. We want to determine, maybe from the partial correlations, what is the distinct contribution of each predictor in this overall model. There's a theoretical reason why we introduce all of them. So we're just going to examine them as a block. What we may choose to do, in fact, what we will do when we talk about hierarchical regression, is we will put in one variable And then we'll create a second block in which we introduce other variables. And then we may create a third block and introduce more variables. What we'll be doing is model building, in which we introduce variables in a way that we can determine their relative significance. Once a certain amount of variability has been explained, do we get an improvement by adding new variables? Twirl open the model settings. And notice that we have two models. The first is model 0, and there's nothing in it. That is the model, the null hypothesis model, where we're predicting with the mean. The second model is model 1. It has all three of our predictors in that second model. If we wanted to, we could click on that green plus button and we could add a second model. But we're not going to do that now. We'll do that with hierarchical regression. So we won't include that second model. We're just going to have model 0 and model 1. There's no changes to make right here, but the overall takeaway is that we are comparing two models. Does our model with the predictor work better than the model that simply predicts with the mean? Twirl open the statistics settings. Under model summary, we want R-squared change, F change, and Durbin-Watson. Under the display, choose model fit, descriptives, part and partial correlation, and collinearity diagnostics. Under coefficients, we have our estimates, confidence intervals, which are set at 95% by default, and also the tolerance and VIF. And then under residuals, statistics, case-wise diagnostics, which we will use a standardized residual greater than 3 as evidence for an outlier, and then get the Mahalanobis test in the lower right. That's for our multivariate outliers. Now, twirl open method specification. We don't need to make any changes right here, but just notice we're using a p-value of 0.05. That's consistent with other analyses that we've done. And then twirl open the plots. Get the residuals versus predicted plot, as well as the QQ plot of standardized residuals. And with that, we can start evaluating our model. Let's first look at the assumptions to make sure all the assumptions have been met. If we simply look at our data set, we can see that all of our variables are scale level, as indicated by the ruler icon next to the name of each variable. We have a random ID number in our first column. That will be useful if we have outliers or some other problematic case. We can find it much easier from that random identifier. We don't have any missing data. Notice there's no empty blocks or cells within our data set. That's good. And our sample size of 200 exceeds the minimum of 20 plus 5K. With 3 predictors, it would be 35. It exceeds that minimum value that we should have. So we know that we have enough people in our data set in order to run this particular model. Now let's take a look at the outliers and see, do we have any outliers? And if so, what are we going to do about them? When we look at the influential cases, we see it is blank. We don't have any univariate outliers, which would be indicated by residual statistics greater than 3 or negative 3. We can see that we do not have any values that meet that criteria. And we also do not have any multivariate outliers, which were identified by a Mahalanobis test. So in this case, all of the assumptions have been met. Now, we didn't actually run these scatter plots. I did this earlier, but let's just see what do the scatter plots look like. We have generally linear relationships. I've talked about some of the problems with that compassion satisfaction variable, some of the places where we should be seeing dots and we are not. But in general, we have roughly linear relationships, and that'll be good enough for using as our predictors. For collinearity, we can look at the tolerance and VIF values. All of the VIF numbers are less than 10. All of the tolerance values are greater than 0.1. So we don't have any issues with collinearity. If we did, we'd want to pay special attention to our collinearity diagnostics, in which we would look at these eigenvalues, and we would use that to interpret the multicollinearity and probably identify which variable would make the most sense to remove from our model. As we're interpreting the independence assumption, we're going to be looking at model 1, not at model 0. So we can see in our Durbin-Watson statistic, the model 1 value for Durbin-Watson is 2.1. That's really close to 2, and that's what we're looking for. Any values less than 1 or greater than 3 would indicate we had a problem. In our residual statistics, we see there is normality of the residuals as indicated by the QQ plot. All of the dots are on that diagonal line. And we also see with our residuals versus predicted plot, a roughly elliptical or round shape of those dots. So we did not have an issue with homoscedasticity. Both of these represent good news in that the assumptions for this model have been met. With that, we can now interpret the model itself. Let's look at the coefficients. So first of all, we are not going to interpret model 0. We're only going to look at model 1. And what we can see is that the R-squared value, the amount of variability predicted, is 0.445. That's our coefficient of determination. We'll turn that into a percentage. 44.5% of the variability in job satisfaction has been explained by our model. That's pretty good. Also note the change in the R-squared is 0.445. The R-squared change is always going to be the same as our overall model R-squared because our first model, our null hypothesis model, predicts with the mean. Any change in our predictive ability by adding predictors is going to be reflected both in the amount of predicted ability and in the change of predictive ability that we see with the R-squared. So we're going to see those two as being the same numbers. The adjusted R-squared tells us something about the population. For our sample, 44.5%, but in the population we'd expect about 43.6% of the variability in job satisfaction could be explained by our model. That's based upon the R-squared value for this model. So we know that there is an improvement in predictive ability based upon adding the 3 predictors that we did for our model. However, we still want to know whether that R-squared change is statistically significant. And to answer that, we're going to look at our ANOVA findings. The ANOVA is comparing our model versus the null hypothesis model. Do we have more predictive ability based upon our predictors than we did with just predicting with the mean? Here we have a statistically significant ANOVA. With 3 and 196 degrees of freedom, we have an F value of 52. That's pretty impressive. We have a p-value less than 0.001. This is a statistically significant model. Our model, with our 3 predictors, predicts better than just using the mean. But we're going to want to take a look at the coefficients for the model so that we can build that predictive equation. As we look at the coefficients, I'll note that we are not going to interpret model 0. We are only interpreting the coefficients for model 1. We have 2 kinds of coefficients, the unstandardized coefficients and the standardized. Let's start with the unstandardized coefficients. The b sub 0, or the y-intercept, is 244.957. That would be the predicted value if all of the other predictors, all 3, were 0. Now that isn't going to happen. There's no such thing as a 0 for job satisfaction, burnout, and compassion satisfaction. So this is not a realistic number in the real world, but it does help with our math. We'll be able to use this number as we make our predictions. We'll definitely have to include this in our model. Our first predictor, unstandardized predictor, is b sub 1. It's a negative 2.691. How do you interpret that? The interpretation of a beta value is that for each 1 point increase in burnout, job satisfaction decreases, this is a negative number, by 2.7 points. The standardized predictor is a negative 0.82. For each 1 standard deviation increase in burnout, job satisfaction decreases by 0.83 standard deviations, controlling for compassion fatigue and compassion satisfaction. Remember, we can interpret those beta values like a z-score, and 0.8 standard deviations, that's a big number. So we can see that there is a big drop in job satisfaction based on increases in burnout. Going back to the model that we're creating, we're going to plug in our B sub 0 from that intercept, 244.957. Our beta, or rather B sub 1, is a negative 2.691. B2 is the 669, and the B3 is negative 0.071. This is the raw form of our predictive model, and when we fill in the coefficients that we pull from our table, it's going to look like this. All right, so let's interpret this. First of all, we can look at these t-values to determine, is this a statistically significant predictor in our model? So you'll note that the t-value for the intercept is statistically significant. This is less than 0.05. But that doesn't really matter in the real world. Even if this value was non-significant, we could still use this model. Burnout is a statistically significant predictor, pretty robust predictor, also less than 0.001. Compassion fatigue, also significant, 0.006 p-value. But compassion satisfaction is not a statistically significant predictor. You'll notice that the p-value is 0.336, so non-significant. And also, what's really weird is the t-value, as well as the unstandardized coefficient, are negative. What does that mean? Do you remember when we looked at the scatter plot between job satisfaction and compassion satisfaction? What we saw was a positive relationship. If you like the feeling of helping, higher job satisfaction. Those two moved together, and that's what we would expect. However, what this model is showing us is that once you control for burnout and compassion fatigue, then the variability left over is actually predicted in the wrong direction, or certainly the unexpected direction. We're seeing a negative relationship between compassion satisfaction and job satisfaction, and that's just kind of weird. What explains that? It's not going to come from the model directly. This is where theory comes in. Why is this happening? We would probably have to spend some time looking at these numbers and seeing if we could come up with some kind of solution. Why do we have a negative relationship with compassion satisfaction and job satisfaction? That just doesn't make sense. But fundamentally, what it's about is that once you've explained burnout and compassion fatigue, that the variability left over is just kind of not worth explaining, or certainly not worth explaining with this predictor. What we would probably end up doing, based upon this finding, is we'd probably just drop that compassion satisfaction variable out of our model, certainly based on what we saw with the scatter plots, what we see with these findings. This is not a robust predictor, and there's something going on with this predictor that is completely unexpected. Looking at our descriptive statistics, we can see the part and partial correlations between job satisfaction and burnout, job satisfaction and compassion fatigue, and job satisfaction and compassion satisfaction. Each of these, the partial correlation, the unique contribution, controlling for the other predictors. Our descriptive statistics are going to be useful for our write-up. One thing we can notice is that all of the predictors have the same sample size. There's no missing data. We'll need the means and standard deviations when we do the multiple regression write-up. And here's what that multiple regression write-up would look like in APA style. We're going to first describe what we did. We used a multiple regression to evaluate the predictive ability of burnout, compassion fatigue, and compassion satisfaction on job satisfaction with our sample of 200 mental health professionals. I then go on to describe the kind of measurements that were used, the professional quality of life scale and the job satisfaction survey, both of which were part of the data collection. Exploratory data analysis. So now I'm explaining all of the assumptions that I checked. I'm reporting the Durbin-Watson statistic. I'm reporting variables like burnout and the tolerance and VIF values for those, showing that I checked these assumptions, the assumptions had been met. Now I explain what happened in the overall model. The model containing burnout, compassion fatigue, and compassion satisfaction was statistically significant, and there's the F values from my ANOVA. It explains 44.5% of the variance in job satisfaction, and I would create a table to show all of these predictors. That table is going to be based largely on the output that I'm getting from JASP. Now a little bit about what I found. As expected, burnout showed a strong negative relationship with job satisfaction. However, when I get down to explaining compassion satisfaction, I say it was a counterintuitive finding, maybe some kind of suppression effect, going in an unexpected direction, and I can report that that contribution was non-significant in my model. What do we take away from all of this? We started with simple linear regression, in which we determined that one variable predicting one outcome gives us a certain amount of predictive validity. However, by adding more predictors and better predictors, we're going to be able to make better predictions. That's multiple linear regression. What we're going to do next is model building using hierarchical regression, in which we'll create individual blocks. We'll put in certain variables. We're going to test those blocks against each other to see which blocks or which block explains the most variability with the fewest number of predictors. Some are going to stay in, some are going to drop out, and we'll discover that as we look at our hierarchical linear regression, which we're going to do next time.